Welcome to this Junior Cycle Higher Level Maths revision video. This video is going to focus on quadratic functions. As part of our quadratic functions revision, we're going to revise function notation and terminology, look at mapping diagrams, revisit the vertical line test for functions. We're going to look at points on a quadratic graph. We're going to look at finding the roots of a quadratic function, and finally graph some quadratic functions.
So let's take a look at a function. So we have here a domain or an input, and it creates output. A function is a rule that creates an output for a given input. In this example, the function is take an input value, so let's take 2, and multiply it by 3, which gives us 6. So this is a mapping diagram, and it represents the function that we've just been talking about. So like I said, a function is a rule that changes the domain value or an input value into a range value. We use the letter X to stand for domain and Y to stand for the range, and this will work as we move forward into seeing them on a coordinate plane, similar to that used when we're dealing with coordinate geometry of the line. So in this case, our function could be written as y equals 3 times x, or f of x is equal to 3x. We'll talk about our function notation in a little more detail in a later slide. So let's look at the terminology in a bit more detail. The domain means the set of inputs. So the domain in this example here to the left is 3, 4, 5, 6, and 8. They're all the inputs, or what we see in the first set in our mapping diagram. The codomain then is the set of all possible outputs. So that's everything we see in the second set of our mapping diagram. That is 0, 1, 2, 7, and 9. The range is then the set of all actual outputs. So notice there on the right hand side of the mapping diagram that the value of 2, although it's there and it could be used, it is not used. So the set of actual outputs are 0, 1, 7, 9. So it is really important that you understand the subtle difference between the codomain, so the possible outputs, versus the range, which is the actual outputs. So let's take a look at a mapping diagram. So here we are given two diagrams. Both of them look quite similar. We have a diagram A and a diagram B. And it's important to note that in this diagram A, that is a function. And this is a function as each element in the domain is mapped to only one element in the range. And that's important. And our focus is on our arrows. So the arrows go one out and it will all land on a value. The second diagram, diagram B, is not a function, and the reason for it is this. Here we have two mappings from one input. So this is not a function as the diamond input is mapped to two different outputs. So let's take an example that might make this a bit clearer. If I put the value of 3 into a formula, I shouldn't sometimes get a 1 and sometimes get a 2. I should only get one specific value. So when I sub it in, I should only get one value out. If I don't, then that is not a function. When we're dealing with with mapping diagrams, like in this case, you're looking out that there is only one arrow coming out of each input. So now let's talk about if the function or relation is not given to us in a mapping diagram. What if we're given instead the picture or the graph? So we have what's called a vertical line test for a function, and it is if any vertical line that is drawn intersects the graph of a relation only once, then it is a function. If this is not true, so if it intersects it more than once, then we have a problem and it is not a function. So let's take this example here. This funny looking squiggle that you maybe don't recognize at this point, and that's fine, but all we need to see is it a function? And the answer is yes, because there's no vertical line I can draw that will touch the graph more than once. this example here, this is not a function, and the reason it is not a function is because when I draw this vertical line, it touches or intersects the graph twice, so it fails the vertical line test. This is also not a function because no matter what line I draw, I can see that there are some that will intersect this relation or graph twice. Therefore, it is not a function. Now let's talk a little bit about function notation. So the most commonly used function notation is this here. This is pronounced f of x is equal to 2x plus 1. F is the function name. X there is our input, and 2x plus 1 is our output, or the rule for an output. So if I told you x was 1, we could then use that rule to calculate our output. Some pieces to note. F of x, this is pronounced f of x. It's important to get used to saying that correctly because it is not f by x, it is not multiplication, it is something very specific. So do get in the habit of saying f of x. F of 2 then will be f bracket 2, and f of x is another way to say y. So y is what they will all be. So y, we think of it as our x and our y axis. But f is more specific to the name. So the analogy I would give is the idea that if you have girls, that would be equivalent to the y, but you wouldn't go around going girl, girl, girl. It's much easier to work with people if they have something that identifies them specifically, and that to us is our name. So I would say Mary, Anne, and so on. So f is the name. It is specifically the name. All of these functions, f of x, it could be g of x, it could be h of x, that's all names, but they are all y's. In the case like all of these are girls. So just be really clear about that. If we want to work with a few functions, we often give them specific names like f of x, g of x, h of x, but they are all a y value. Another type of function notation you'll see is this, and this is f is the function such that x is mapped to 2x plus 1. Now, at junior cert higher level, you will see this in a form like this, but my suggestion would be to always rewrite it as our above f of x. If you were wondering why we even have this, this becomes a much more useful notation as we move into Leaving Cert higher level. So just like before, f is our function name, x is our input, and 2x plus 1 is our output. So my advice to you is if you see something like this, that you come along and rewrite it as f of x equals 2x plus 1, because this is the most useful format for us, and this is going to be the one that will help us work through the questions.
The word quadratic comes from the word quad, meaning square, because all quadratics have a variable squared. Usually the variable is x, so quadratics can be identified by having an x squared. This is important because often students get confused as to what exactly makes an equation or a function quadratic. We can also say that it has degree 2 because of that power 2 on the x.
Now let's talk about quadratic functions. So quadratic is something which you would have seen a huge amount of in algebra, and it's really important that you understand how all the stuff that we've done in algebra also then links into the function space. So this graph I have on the left is a positive quadratic, and positive will mean that the a value is greater than 0, or the leading coefficient is greater than 0, or positive when I'm dealing with ax squared plus bx plus c. So basically what I'm saying is that this piece here, that is going to be positive for that graph. On the right hand side then, this graph is a negative quadratic. So a will be less than 0 or a will be negative, or the leading coefficient will be negative. So in this case, my a here will be negative. That is how we can identify from the actual function themselves and from the graph. A great way to think of this is that positive people smile, so our positive graph looks like a smiley face, and negative people frown. So our negative there looks like a frowny face. So be aware of how you can identify both the function graphs and from basically the function notation that it's given, how we would figure out if it's positive or negative. So these 2 points here are called our roots, and we have the equivalent here on the negative side as well. The roots are where the graph itself cuts the x-axis. So when we were dealing with coordinate geometry, the line, we didn't refer to it as our root, we called it our x-intercept. We're going to use the term root now as we work through quadratics because it is a better use, it's a better word to use, and you'll see it a lot more often as we work through questions. We then have what's called the y-intercept. Here it is in blue on both graphs. This is where the graph cuts the y-axis. So we saw that in coordinate geometry, the line, and we would have known that to get the y-intercept, we would have let x equal 0. The third thing that you might be able to see here is in yellow, and on the positive graph we have what's called a minimum turning point. On the negative graph we have what's called a maximum turning point. So now, let's talk about finding the roots of a quadratic function. So we talked about the roots being these 2 points here, and they're equivalent to what we would have called the x-intercepts as we worked with the equation of the line in coordinate geometry. So here they've asked us to find f of x equals 0. So remember, f of x is another way to say y equals 0. And just like when we were in coordinate geometry of the line, if we let y equal 0, we got the x-intercept. So my f of x is 2x squared plus x minus 6, and I want that equal to 0. At this point, you might go, oh, this looks familiar to me. And the reason it probably looks familiar is because now what we have is a quadratic equation, and what we're being asked is to solve it. So anytime we're solving a quadratic equation in algebra, we're doing the exact same thing as finding the roots of a quadratic function in the function space. It is the exact same question, just asked in a different way. So we have 2 methods of doing this. Since they've given us no indication about how to give our answer and in what kind of form, we can assume that both are valid. So the first way that we can do is to work using factorization. The second is by using the quadratic formula or minus b formula. I'm going to work with factorization, so I'm going to use the guide number method. So the guide number in this case is the first multiplied by the last, which is 2 by minus 6, which is minus 12. So that is my guide number. And I need to factorize that such that I get a plus 1 when I add them together. So minus means different signs. So one is going to be positive and one is going to be negative. So if I say 4 and 3, where 4 is a plus and 3 is a minus, that will add up and give me a plus 1, which is what I'm looking for. Remember, the purpose of this is I'm trying to separate this plus x into 2 pieces so I can do grouping. So 2x squared plus 4x minus 3x minus 6 equals 0. At this point, I would suggest to you to double check, does plus 4x minus 3x, does that give me plus x? A lot of times students making very silly mistakes with signs. Please double check at that point. Everything now is fine. Take out a 2x, which is common. I'm left with x plus 2 minus 3, and I'm left with an x plus 2. At this point, my check is, are my brackets the same? They are. That means I'm going on the right track. So I get 2x minus 3, x plus 2 equals 0. So now I'm going to let each factor equal 0. So I get 2x minus 3 equals 0, which gives me 2x equals 3 as I add 3 to both sides, and x equals 3 over 2, or if you prefer, You can write that as 1.5. Then I get x plus 2 equals 0. And I'm going to subtract a 2 from both sides, and I get x equals minus 2. So what we have here is the roots, and in this case there's my minus 2, and here's my 1.5, and this is the function f of x is equal to 2x squared plus x minus 6. So it's so important that you see the connection between solving quadratics, which you've been doing probably since second year, and working with the quadratic functions, which is possibly a little bit newer to you. Now let's work with an example of graphing a quadratic function. So draw this function y is equal to 2 minus x squared in the domain minus 2 is less than or equal to x is less than or equal to 2. So just to take a look at this is a negative quadratic. So straight away I know when I draw it, it's going to be this frowny face here. How I know it's negative is I look at the x squared part and I see that the leading coefficient is negative. So one way to think of this is which thing has the biggest power. So it's x to the power of 2, so it has the big power. So the one that has all the power, when that is negative, the whole thing is negative. When that is positive, the whole thing is positive. So we're going to work with our little table and see. So I've already filled in my table. The first column is my x, which goes between minus 2 and 2, and that's coming from my domain here. I then fill in my actual function itself, which is y is equal to 2 minus x squared. Remember to put all those values in as brackets squared. That gives me a y value, and then it gives me a point. So I'm going to go straight to plotting my point. So I get a minus 2 minus 2. I have a minus 1, 1. I have a 0, 2. I have a 1, 1. And I have 2 minus 2. So I want to draw this. Again, please bear with me. I'm on the computer and it's quite hard to draw. And we get something like this. And I label this y is equal to 2 minus x squared. And this does look like the negative quadratic that I predicted it looked like. Do note that when we're drawing a quadratic function, you cannot, under any circumstances, use your ruler. This is a curve. Every piece of it should be very curved, and if they think in an exam that you've used any kind of ruler or it's too flat, you will be docked marks. So you want this lovely curve. It doesn't have to be perfect. Mine is definitely not perfect here, but it's the best I can do on the computer. You could probably do a lot better on your page, but you're not looking for perfection. We're just looking for that lovely curve.
Let's look at an exam style question. This is from the old junior certificate course, but will give you a good chance to see the types of questions that we were asked previously. So we have 3 graphs here, and they have told us that we are dealing with one particular equation. The equation is x squared minus x minus 2 equals 0. They told us that the solution to this particular equation were x equals minus 1 and x equals 2. These are the roots. And if you look at our graphs, we should be able to see that the roots are x equals minus 1 and x equals 2. So graph A looks fine. Graph B, x equals minus 1, x equals 2. That's perfect. But graph C, x equals minus 2 and x equals 1. These are the wrong way around. So C is definitely incorrect. So this is the first step in trying to figure out which of the 3 graphs is correct. We're now left with 2 graphs, graph A and graph B. Both have the correct roots, the roots being x equals minus 1 and x equals 2. So we need one other piece of information to try and match the graph correctly. The easiest way to do this is to focus on the constant, the number without an x in the equation, that is minus 2. That will always be represented on a graph as the y-intercept. So in graph A, the y-intercept is minus 2, while in graph B, it looks to be about negative 3. So this graph B is incorrect, meaning the correct function is graph A, and the reason is because the roots are correct. So roots are x equals -1 and x equals 2, and the second one is the y-intercept, so that is equal to the constant. So this is equal to -2. Remember, when you're asked for a justification or a reason, this is only to show that you have a made a guess. So you don't have to write big long paragraphs, you just need to explain your logic. Using maths is often the easiest way to do this. Let's look at another exam question. This is from the 2014 Junior Certificate paper. It is given, this question has given us two functions, so f of x and g of x, and has given us two graphs. And we're trying to match the correct function to the correct graph. Looking at the graphs first, hopefully you can identify that this on the left is a positive graph. Remember, positive people smile. And this graph on the right is a negative graph. So if we can figure out which of the functions is positive and which of the functions is negative, we'll be able to match them to the correct graph. Looking at f of x, we look at the x squared term. The x squared term is positive, meaning that this function is positive. For g of x, the x squared term is negative. So apologies. So the g of x, the x squared term is negative, meaning that this function is negative. The way I like to think about this is we look at the variable with all the power, and that variable with all the power has the power to decide if it's going to be positive or negative. So if that, in this case x squared, is positive, the whole thing is positive. If the x squared is negative, the whole thing is negative. So that gives us the positive f of x and the negative g of x. There is a second way that you can do this. However, I would stress the importance of understanding how to tell if a function written in the form f of x or g of x is positive or negative. But the second way we can look at this is by looking at the constant. So here the constant is -3, here the constant is +3. Remember that the constant represents the y-intercept. So here it's about -3, on this graph it's about +3. That's another way you can use for this particular question, and also a way you can double check that you're correct. Another, match the function to the graph. In this question, which was from the 2013 paper, we were given three different quadratic functions: f of x, g of x, and h of x. They are all quadratic, although sometimes students struggle with the fact that h of x is quadratic. H of x is missing a constant. It has an x squared term and an x term, but it has no constant term. It's still a quadratic because remember, what makes something quadratic is the fact it has an x squared. If something like h of x doesn't have three terms, it means it's not a quadratic trinomial, but it is still quadratic, which means it still has the same shape graph. So we have 6 graphs. So the first thing I'm going to do is go through my graphs and mark them as positive or negative. So diagram 1 is negative, 2 is positive, 3 is positive, 4 is positive, 5 is positive, and 6 is negative. Remember, positive people smile, negative people frown. Looking at my three functions, f of x, it has 2x squared, so that's positive. G of x is x squared, so it's positive, and h of x is x squared, which means it's positive. So actually all three of our graphs are positive, meaning we're going to disregard our negative graphs straight away. So the next thing we can do is to look at the y-intercept and see if that can be helpful to try figure out which graph is which. Remember, the y-intercept on the graph is represented by the constant in the function. So let's start with f of x. So f of x is -6. So is there a graph that cuts the y-axis at -6? And this one looks the closest. because this one is at 0. So diagram 2 is at 0. Diagram 3 is somewhere in the negative. Diagram 4 is also at 0, and diagram 5 is some positive number. So even though they haven't given us numbers on the graph, we should be able to identify where we're in the positive part of the y-axis and where we're in the negative part. So this is f of x. For g of x, we have plus 9, so it's the positive part. And diagram 5 was the only place where we had a y-intercept that was a positive part. So this is g of x. For h of x, it's a little bit trickier because there's no constant. But no constant is like having a plus 0. So that means that the y-intercept is going to be 0. When we have a quadratic in that form, we're always going to be going through the origin. Now, we have a little bit of an issue here because we have two diagrams left that are both positive and both have a 0 as the y-intercept. So diagram 2 and diagram 4. So what we're trying to understand is, well, which one is which? So we've used the fact that they're positive. We've used the fact that they cross the y-axis at 0. So the last thing we can do is actually look at the roots themselves. Now, I've taken this part from a question, and in the first part of this question, we were asked to solve h of x equals 0. We were asked to do that for f of x and g of x as well. But let's focus on that. If we solve h of x equal to 0, we're saying h of x is x squared minus 2x, and we want that equal to 0. So what we're doing is we're actually finding the roots. Remember, this is not a quadratic trinomial, so we're not going to be using our guide number method or any other, maybe you're using trial and error there. Instead, what we're going to do, we're going to use highest common factor. So we have an x here, leaving me with x minus 2 equals 0. So our zero product property tells us that either x equals 0 or x minus 2 equals 0. Remember, any two numbers multiplied together, giving us an answer of 0, one of the numbers must be 0. So I'm going to add a 2 to both sides. And when I do that, I'm left with x equals 2. So for h of x, the two roots are x equals 0 and x equals 2. So the one that best represents that is diagram 2, because the second root is definitely positive. If we look at diagram 4, the second root is negative. So it's not diagram 4. So remember, like I said, you would have already had that part done. It was already worked out. Well, you would have already worked it out in the first part of this question, but it's good to see all the different ways that we can tell which graph links to which function.
So now let's look at an example where we're still working with the quadratic function, but we're working with it in a slightly more challenging way. So part of the graph of the function y is equal to x squared plus ax plus b, where a and b are elements of z, which stands for our integers, which means they're positive or negative whole numbers, is shown below. The points R and S are on the curve. Use the given points to form two equations in A and B. So this leads us to a very important fact, which we've already seen in coordinate geometry of the line, and that is, if a point exists on a line or on a curve or any type of function, we can substitute in that point for x and y into the equation and it will work, as in the left hand side will equal the right hand side. So let's work first of all with the point R. So the point R is 2, 3. This gives me the x part and the y part. The function itself is given as y equals x squared plus ax plus b, which gives us, instead of y, we're saying 3 equals x squared, so 2 squared, plus a times 2 plus b. So we can clean that up a little bit. So we get 3 is equal to 4 plus 2a plus b, and cleaning it up just a little bit more, we get 2a plus b is equal to minus 1, so subtracting a 4 from both sides, and that gives us equation 1. We can do the same thing again for our second point, which is s, and that s is minus 5 minus 4, which again is our x and our y. Our equation is y, which is minus 4, is equal to x squared, so minus 5 squared, plus a times minus 5 plus b. And working that through, it cleans up to minus 5a plus b is equal to minus 29. So when we work through this, minus 5 squared will give us 25, and we would subtract that from both sides. So that gives us our second equation in A and B. Now we've been asked to solve your equations to find the values of A and B. I have two equations and two unknowns, so we're using simultaneous equations. We can use any method that we have, and we've gone through some methods in the algebra module to do this. The most straightforward and likely method that people will go to is elimination, so we get one of our values to eliminate. The easiest thing to eliminate here is our b's, and we can do this by multiplying the bottom line by minus 1. So we get the top line is unchanged, 2a plus b equals minus 1. Multiplying that across, I get 5a minus b equals 29. The b's end up cancelling, so plus b minus b is effectively 0. And working this, I get 7a is equal to 28. Dividing both sides by 7 will give us a equals 4. We now go back to either equation. I'm going to take equation 1, which is 2a plus b equals minus 1, and we're going to sub a. Instead of a, we're going to sub in 4, so 2 times 4 plus b equals minus 1. So that gives me 8 plus b equals minus 1. Subtract an 8 from both sides, and we get b is equal to minus 1 minus 8. B is equal to minus 9. So what we actually have here is the quadratic equation y equals x squared plus 4x minus 9. And if you want to just take a quick look at the graph and see, does that make sense? Well, the first thing I would look at is that constant, that minus 9 is the y-intercept, and at least it's in the right part of the graph. We don't have any other information we can work out at this point, but that's enough for me to say, well, look, there's nothing obviously wrong. So now we extend this, and it asks us to write down the coordinates of the point where the curve crosses the y-axis. So we've just talked about this. Just to remind you, y is equal to x squared plus 4x minus 9. If I want to find where it crosses the y-axis, or the y-intercept, our rule is we let x equal 0. The same rule that we have when we're dealing with coordinate geometry of the line. So y is equal to 0 squared plus 4 times 0 minus 9. So y is equal to minus 9. But that's not enough. They want the coordinates of the point. So we write this as 0 minus 9. You could have also just looked at the constant part, the bit without the x, and that would have given us the point that we're looking for, which is here. So that point here is 0 minus 9. The last part of this is by solving an equation, find the points where the curve crosses the x-axis. So here what we're looking for are the roots of the quadratic, or what we would have called these when we were dealing with the line is the x-intercepts. So to do this, we let y equal 0, which gives us x squared plus 4x minus 9 equals 0. So effectively we're solving this quadratic to find two values of x. So notice that the question said, give each answer correct to one decimal place. If you can remember back when we were working through the algebra module, what we said was if there was ever a quadratic that gave you a hint such as correct to so many decimal places or in third form, it was important to note that this was a big hint to you, telling you that you had to use the quadratic formula. So the quadratic formula is also known as the minus b formula, and it's found on page 20 of your log tables. So the minus b formula is x equals minus b plus or minus square root of b squared minus 4ac all over 2a, where we're given ax squared plus bx plus c. So we can work from this saying a is the coefficient of the x squared, which is 1, b is the coefficient of x, which is 4, and c is the constant, which is minus 9. So x is equal to minus 4 plus or minus square root 4 squared minus 4 times 1 times minus 9 all over 2 times 1. Cleaning that up, we get x equals minus 4 plus or minus square root 16 minus 4 times minus 9 is plus 36 all over 2. And then we get x is equal to minus 4 plus or minus square root of 52 all over 2. We can simplify minus 4 plus or minus, and this simplifies down to 2 root 13 all over 2, and this is x equals minus 2 plus or minus the square root of 13. So if you're asked in third form, that's our two answers. We can simplify this now taking the plus and taking the minus, and then we can work out our two answers correct to one decimal place.